Hello. So I'm going to begin today by fixing and doing some things from last time. So let's call this mistakes and omissions. Okay. So first, the mistakes. So I neglected last time when I was talking about, I'm not going to go through in detail to restate everything, but last time we talked about a pointwise, we talked about approximate identities and various kinds of convergence you get by convolution with approximate identities. And one of the cases we looked at was a case where you get pointwise convergence. So when talking about pointwise convergence using convolution with approximate identities, right, so there's a restriction that one has to put on the approximate identities in order for that pointwise convergence result to hold. And that also eliminates the possibility of a certain thing that I stated last time from possibly being true. So I'll state two things. The approximate identity and remember that an approximate identity is a sequence of signals satisfying certain conditions. And to get this pointwise convergence conclusion that I talked about last time, the approximate identities need to be even. Okay. And just to make sure we know what that means, so you must have that uj of t is equal to uj of minus t. Okay, and so this must hold both in the periodic and aperiodic case. Okay, and so all of the approximate identities that I talked about last time had this evenness property. Okay, but you do need to assume that. And the other thing that happens is because of this condition, you can't have that result for the approximate identities on the positive half-line. And so I had admitted that when I first stated the convergence results on the positive half-line, and then I just decided that it should have been there, but that was a mistake. So the resulting, so let me say it this way. In consequence, one cannot have the same sort of pointwise convergent results. You can have other kinds of pointwise convergence results, but just not in the form that we stated last time. Okay. So I admitted a hypothesis here that, and this hypothesis, moreover, ensures that one of the things I said was true is not true. Okay, so those are the mistakes, or at least the ones that I could think about afterwards. Excuse me. Omissions. So I waffled about this, and then afterwards I realized that I should really have written this thing down. And so the periodic Dirichlet kernel came up when I talked about the Fegge kernel. So again, I'm not going to write down all of the background here because I did that last time. But we had two Fegge kernels, one an aperiodic one, which I wrote like that, and one which was a periodic one, which I wrote like that. And I always get this mixed up whether I go TN or NT. Thankfully, it isn't crucial. Okay, and then what I did write down is I wrote down a formula for the periodification, the T periodification of the aperiodic Fegge kernel, and showed that it was closely connected to, and very closely connected to, the periodic Fegge kernel. With the very closeness happening when there was a nice relationship between omega and T. Okay. Involved in that formula, which related the periodification of the aperiodic Fegge kernel to the periodic Fegge kernel, was the periodic Dirichlet kernel. So I am going to write that one down again. Here's the formula for it. Because and what I didn't do and should have done was talk about the aperiodic Dirichlet kernel, because that's interesting as well. I almost talked about it, but not quite. Okay, so I wrote this formula down last time. And so at times which are not integer multiples of the period t, and I'll also see for consistency, I repeated not putting the denominator in this time. And so it's sine pi t over t, okay? And had integer multiples of the period, it looks like that. All right, so so what I didn't do last time was write down the aperiodic Dirichlet kernel, and the formula for that one is and so the notation here is designed to duplicate the notation for the Fegge kernel, but for D instead of F. And so the formula is sine 2 pi omega t over sine, this one's not periodic, pi t, right? And at 0, it has the value 2 omega for continuity. Okay, so this is for t not equal to 0, and this is for t equal to 0. Okay. So as I said, when you periodify the aperiodic Fegge kernel, what you get in general is you get a linear combination of the periodic Fegge kernel and the periodic Dirichlet kernel, with the coefficient of the periodic Dirichlet kernel vanishing for situations where omega t and n satisfy some convenient relationship. Namely, I think it was that n is t omega, I think. Okay. All right. So, but what I want to do now is talk a little bit about the Dirichlet kernel. Okay. And what I want to do is I want to produce a formula which shows that the periodification of this is again related to the periodic Dirichlet kernel, with kind of an error term which vanishes when t, omega, and n have appropriate satisfy appropriate properties. Okay. And so one can show, it's hard to find these formulas, but they're interesting, so I do want to write them down. So what you get here is you get a different kind of a formula for the Dirichlet kernel than you did for the Fege kernel. Depending on whether omega is an integer multiple of the frequency associated with the period. Okay, so you get 1 over t d per t n of t, and this is valid when when omega is not an integer multiple of 1 over t. Okay, and then you get something slightly different. When the frequency omega is an integer multiple of 1 over t, right? So to prove this formula is a bit of a tedious exercise using contour integration, but you can do that. Okay. Okay, and so there's other things I wanted to say about the Dirichlet kernel. The Dirichlet kernels. Fact is, and that's why these didn't kind of make the list in my first cut, is neither of these are approximate identities. Okay, so d omega is not an approximate identity, and so maybe I'll be clear about that. What I mean is this. Okay, so if you replace this real parameter capital omega with an integer parameter j, and then think of letting omega or j go to infinity, for the Fege kernel and the Poisson kernel, that gave rise to an approximate identity, but that's not true for the Dirichlet kernel. And d per t n as n now is your index is not a periodic approximate identity. Okay, and this is for slightly different reasons in each case, and different but related reasons. Okay, so let's first look at the aperiodic Dirichlet kernels first. Okay, so here they are here, right? So I talked last time about this sinc function. Okay, and I told you that that was an example of a function that was not in L1, but was conditionally integrable. Well, this is a close relationship with the sinc function, and so it's not in L1. Okay, so D omega is not in L1. Okay, so that's in the aperiodic case. All right, so one of the conditions in the aperiodic case was that all the signals in your sequence, which you called an approximate identity, had to be in L1. Right? You had to perform certain convolutions with them. All right. And in the periodic case, all right, so here was our Dirichlet kernel there. So this thing is a bounded continuous function on each period. And so therefore it's in an L1 on each period. So this is in L1 per, okay? It's a periodic function which is in L1 on each period. Okay, but the condition that these do not satisfy in the periodic case is that, remember, one of the conditions for an approximate identity was that for the index parameter here, which is n, not j, there had to be a uniform bound for the L1 norms, okay, and that's what fails to be satisfied here. And it's because the limit as n goes to infinity of the L1 norm of the periodic Dirichlet kernel is infinity. Let me write my regular infinity, not that made up one. Okay, all right. And so the Dirichlet kernels are not approximate identities, and this is going to come back to us in force when we talk about Fourier analysis and convergence of Fourier integrals and Fourier series, and at the core of both of those subjects and the reasons why that they are complicated is exactly this fact that these are not approximate identities. Okay, but we'll get there when we get there. Okay, so now let me talk about approximation and regularization. So I talked about approximation. Now we're going to extend the approximation to include regularization, and as I sort of suggested last time, what we're going to see is that there's a very regular class of signals that are dense in almost everything. So approximation and regularization. Okay. All right. So last time we spent most of our time talking about approximation, and we particularly talked about approximate identities. Now we're going to combine that to get a different and very surprisingly strong approximation results by very regular functions. All right. So let me be specific about that. We will show that one can approximate large classes of signals and distributions by sequences in kind of the smallest class of signals that we're talking about, which is the compactly supported infinitely differentiable signals. Okay. So the first thing that we want to look at is we want to look at if you take a regular convolution, let's say, of signals f and g, okay, and f and g have some regularity properties. So maybe f is differentiable. When does the regularity of f or g, convolution is commutative, so it doesn't matter if it's f or g. When do the regularity properties apply to the convolution? Okay, so I'm going to state first a general sort of a condition along those lines. Okay, and the condition is going to be this. So let f and g be measurable. And satisfy one. Okay, so I'm going to ask that f is locally absolutely continuous, and we talked about this before, and I'll write down what the condition for that is again. It means that f of t is equal to f of 0 plus, and the choice of 0 here is arbitrary. You could choose any other number. Okay, and so the idea is that there's an integrable function f prime, which isn't quite necessarily the derivative of f, but it sort of is in exactly the sense that f is the indefinite integral of its sort of derivative f prime. But the main feature is this thing is locally integrable. Okay, and so f is the indefinite integral of a locally integrable function. That's what it means to be locally absolutely continuous. Right, so you should think of, if you want to, f as being continuously differentiable, if you want to simplify life. Okay, and for each compact k in R, okay, these two functions now, s and t maps to f of t minus s, so the argument of the convolution integral of f and g, and the other one is the argument of the convolution integral of f prime and g. Okay, so these are integrable on k cross R. Okay, so the idea is that they're locally integrable here and integrable here. Okay. All right. So then, if this is true, okay, f and g and f prime and g are convolvable. Okay, the convolution is locally absolutely continuous. Okay, meaning it has a locally integrable derivative. Okay, I say that sloppily. I mean that it has there's a function f star g prime, which is locally integrable, and f star g is given by a formula like that. Okay. Okay, and this locally integrable function f star g prime, which gives the local absolute continuity of f star g, is f prime star G, okay? And so you see here that the regularity of F transfers to the regularity of the convolution, right? Okay, and as you can kind of see by the hypotheses here, if you're familiar with Fubini's theorem, this is sort of a direct application of Fubini's theorem, and the there's a kind of standard condition about swapping derivatives and integrals. Derivatives and integrals. Well, the convolution integral. Where the convolution is defined by an integral, and you kind of want to move the derivative inside the integral. So there's standard results about doing that that I haven't stated. It won't. Okay, but this is true. Okay, and so there's some special cases of that we'll think about. All right. So if G is in L1, and if F in CK, let's say, of RF, so it has to be K times continuously differentiable, and I'm also going to ask that all of its derivatives be bounded functions, okay? Okay, so then so certainly here F and G are convolvable, right? F is bounded and G is in L1, and if you take a look at the conditions that we have had for convolvability, this will give you convolvability of the pair FG. But moreover, F J G is convolvable, and so it's convolvable. It is so sorry, I need to say here J in 0, 1, K. F star G is CK. Okay, and so again, the point is that the regularity of F transfers to the convolution, under hypotheses. Okay, and the derivative of the convolution is the convolution of the derivatives in the appropriate way. Okay, so F star G, J's derivative is F, J's derivative star G. Okay. All right. Okay, and you have, without saying it explicitly, let me just say that you have analogous results for periodic signals. Okay, all right. And so they read rather exactly the same. Okay. So what's the point here? The point here, so as a consequence, if f let's say is if f is in L1, okay, and it needs to be in L, it needs, I'm going to state a weak version of this. So if f is in L1, and this is just to make sure that convolutions exist. Okay, actually, I'm going to state the result that I want here, even though it's not exactly directly connected to the way I stated this theorem. Okay, we can easily see why it's true. And so let me state the thing that I want. So if f is in L1 loc, okay, and so that's different from what I did here, where I assumed that f, where I assumed that g was in L1, okay. I'm going to take f in L1 loc, and g here, I'm going to take to be in this space. Okay, then f star g is, well, in E, this space of test signals E, which remember was just C infinity, right? Instead of all infinitely differentiable signals. Okay, and this doesn't just quite follow from the corollary in the way that I've stated it, again, because G is in L1, but it does actually follow from the theorem, because I have this compactness condition here. Okay, and G, the way I've given it, G has compact support, and so you're going to be able to verify condition 2. Okay. All right, so this is the regularity part of approximation and regularization, right? I can take a very irregular signal f and convolve it with a very regular signal g, and what comes out is something very regular. What I don't get, however, is I don't get the support conditions on g being transferred to the convolution, okay? All right, so it's not the case that this is in D. Right. Okay, and also there's a periodic version of this. If F is in L1 per T, and G is in D per T. Okay, so what do I get? So I get that the convolution is infinitely differentiable, but it's also periodic, right? Because the periodic convolution of periodic signals is periodic. And so it's infinitely differentiable and periodic. So it's actually in D per. Okay, so you get a little bit stronger conclusion here than you do in the aperiodic case. Okay, so now we wish to combine the approximation and regularization, the separate approximation and regularization results to get approximation by signals in D, right? Okay, so here's how you do that. First, what you need is you need a class of signals, which we're going to take a class of signals in here, well, in here or in the periodic case, or here in the aperiodic case, which converges to the Dirac. Okay, so this is, in other words, and when I say converges to the Dirac, I mean in the sense of convergence to distributions. Okay, so let's let phi be, actually, let me not call it phi because I don't want it to be too generic. Let me call it rho, be a test signal. Okay. And I'm going to, just because you can always do this without loss of generality, I'm going to ask that this be even. Okay. All right. So then, and I'm also, and this is easy, you can just normalize it if it's not true. I'm going to ask that it's integral equal to 1, because what I'm going to do is I'm going to build an approximate unit from this. I'm going to define rho j to be the same thing that I did with general signals in L1 last time. I'm going to define a sequence like this. All right, and then if I do that, then this is an approximate identity. Okay. All right, so the idea is that okay, for small values of j, I have this infinitely differentiable thing that sort of looks like this, and as j gets larger, they sort of tend to become more and more concentrated about 0. Okay. All right, so the situation is rather like I described last time, using approximate identities, but now my approximate identity is in not just L1, but D, so it's infinitely differentiable with compact support. Okay. Now, if F is an element, let me say this. So I'm also going to choose not an approximate identity, but what I call a special approximate unit. Okay, so also let psi j be a special approximate unit. Okay, and so let me just remind you what that is by drawing what that means. Okay, so the idea is that the first one is 1 on some compact interval like so, and then it's in these things are all in D, and so they have to be cut off like so, and then as j gets larger, they get the domain on which they're identically equal to 1 grows. That's still curtails. And so they had to have this condition that they took the value identically 1 on larger and larger, but still compact subsets. And there was also a condition about uniform boundedness of the derivatives of the terms in the sequence, and that can be achieved just as I sort of drawn it here by taking these things to be chopped off to 0 in the same way. Okay, so I choose a special approximate unit. All right, so now if f is a signal or a distribution, okay, we have the signal or distribution psi j f. Okay, all right, and so if it's a function, then this just means standard multiplication. Okay, and if f is a distribution, this means multiplication of a distribution by an infinitely differentiable function, and we know how to do that. Okay, and so the idea here is that you're going to take f, which is defined on all of R, and you're going to cut it off. Okay, outside, and as j gets larger, you're going to cut it off to 0 outside, this, compact sets that get larger and larger as j gets larger. Okay, so the idea is that these things, as j goes to infinity, in some sort of way, they converge to f. Okay. All right, and for all of the signal spaces or distribution spaces that we have been talking about, it's always going to be the case that this product, okay, will be in the same space that we started with, right? And that's just because of the particular properties of these special approximate units psi j. So if f is in LP loc, then the product will be in LP loc. If f is a distribution in D prime, then soon will be in D prime. Okay. Then define rho j convolved with psi j f. Okay, now notice that if f is locally integrable, okay, so that's kind of the biggest class of signals that we could talk about, then this convolution will always exist. Okay, this thing and this thing will be convolvable, and it will be convolvable because both of these things have compact support and f is locally integrable. Right, so if you look at the the formula that defines convolution or convolvability, you'll see this thing will always be this pair will always be convolvable. So I can always calculate that thing. Okay, and similarly, if f is a distribution, okay, this will now be a distribution with compact support because each of these psi j's has compact support. So then I'm taking, and this also has compact support. So I'm really taking the convolution of two distributions with compact support, right? So as distributions, those will be convolvable, right? So the point is this convolution you can always calculate. Okay, and so then, really wants me to plug it in, I'm almost done. So then this converges to f in all of the function spaces that we've been talking about. Like LP, okay, and in D prime for distributions. Okay, so this thing, by my regularization result, will be infinitely differentiable because this has compact support and this has compact support. It will also have compact support. Okay, and so therefore what I've done is the terms in this approximating sequence are elements of D. Okay, and so this thing is in D. All right. And so that kind of gets me the very special approximation and convolution and regularization results that I talked about. And also this also holds with appropriate modification. In the periodic case. Okay. All right, so that finishes everything I wanted to say about convolution. So I talked about a lot of stuff there, and we're going to see more applications of convolution as time goes by. But I wanted to, without giving proofs, because that the whole sort of 5-ish lectures that I've given on convolution would be a course in itself with proofs, but sort of give the main highlights of the theory and some of the applications of convolution, because they are wide and deep. And so I covered a lot of material there, not all of which I actually covered when I actually teach the course. But given the sort of freedom of this loosey-goosey format, I wanted to put it out there so that anybody who cares can at least get a sort of very quick introduction, a survey of what's known. Okay. All right. So next time what we will do is we'll start down the road to talking about things Fourier. Okay. So next time we start with our Fourier stuff.